Hi everyone, welcome back to our channel. Last video we talked about the basics of end-to-end encryption and keys. However, today we're going to be going more in depth into the maths behind this process and how these keys are formed and then used. As a summary for the last video, let's just go over what we learned. So we said that if someone wants to send a message and keep it secure from public viewing, they can encode it using a public key that anyone can access. This will convert the plain text message into an encoded ciphertext that gets sent to the receiver, and then once the receiver receives this, they can then decode it using a private key only they have to convert the ciphertext back into the original plain text message. In this way, the message remains secure and can only be seen by the sender and receiver, as the rest of the time it is encrypted, aka it is in the ciphertext form, not the plain text one. So now we've gone over what we talked about last time, let's get into the more practical part of encryption and move away from the theoretical. What we're going to be focusing on today is called RSA encryption, which is one of the most common methods for key generation. It consists of 6 relatively straightforward mathematical steps and results in a public key that encrypts and a private key that decrypts, and this is specifically for end-to-end encryption. Although we will not be going over the reason why these mathematical steps actually work, we'll leave a link in the description if you would like to read up more on this. Okay, so step 1, we choose 2 prime numbers. In practice, these are usually very large in order to make hacking even more difficult. However, for our case, let's use 11 and 13 and call these P and Q. So P equals 11, Q equals 13. Note that we're going to be recording the variable values we found throughout our example up here so that you can keep track of what we're doing. Step 2. Next, we need to multiply the 2 primes we found, P and Q, in order to create a variable n. So we can say n equals P times Q equals 11 times 13 in our example equals 143. And again, we've recorded that up here as well. Note that n is publicized, however P and Q are not. This means that for very large prime factors, P and Q, it is extremely difficult to derive them from n. So even though people can potentially see n, the message remains secure. Let's say, for example, n equals this very long number, so 30 digits long. It is almost impossible for a hacker to find the prime factors of this number, as even the smallest prime factor, in this case p, is 14 digits long. We, in fact, know the values of p and q are as such. However, this would be very difficult for a hacker to find just by knowing n. We in fact attempted to find the prime factors of this value of n on a Python program, and we found that in the end it took over 2 days, and we even had to kill the program as it was taking so long. Note that in general, the length of n does not matter so much, because if the number n was very large, such as this one, but its prime factors were something like 2 and any other number, it would not take too long to crack. Once you have found the smallest prime factor, so in this case 2, you can then simply divide n by it in order to find the second prime factor. So in essence, what matters more than the length of n is the length of the smallest prime factor, as the longer it is, the harder it is to find P and Q from N. In order to prove this, we then decided to create a more in-depth program in which we analyzed the time taken to find the prime factors, P and Q, where the smallest prime factor, which we set as P, increased in length each time. We found that the time to find the prime factors increased many-fold as the digits of the smallest prime factor increased. And this can be seen through the data and the chart presented on the slide. For example, here, when P was only 5 digits long, it only took 0.03 seconds to find P and Q from N. However, once it was 10 digits long, it took around a day and a half. Note that the chart over here shows this data more visually. However, it is displaying the log of the time we calculated in seconds. Of course, this time can change on different computers in different settings. However, this is only an illustration of how the time increases exponentially as the number of digits of the lowest prime factor increases. We have also linked the GitHub wherein we provide the code that we used for this program down below in the description if you would like to take a look. So now moving on to step 3. Let's first define what coprime means, as this becomes very important to RSA. Coprime means that two or more numbers have no positive integer factors in common, ignoring one as a factor. So for example, 2 and 7 would be coprime, as they share no factors, except one which we ignore. 4 and 6, however, would not be coprime, as they share the factor 2, aka both are multiples of 2. So now let's come back to what we need to do in this step, in step 3. We need to find the number of integers up to n, not including n itself, that are coprime with it, meaning, as we said before, they share no factors excluding 1. So for example, let's consider a small number instead of our value up here of n equals 143, in order to simply illustrate the mechanics of finding this number of integers up to n that are coprime. Let's call this number x and say x equals 15. So first thing we'd do is we'd list the integers up to x, not including x itself. So this would be 1, 2, 3, 4, all the way up to 14. Then we would see if any of these share factors with 15's factors, not including the trivial factor of 1. So although we know that 15 has the factors 1, 3, 5, and 15, we are not looking at 1. So now we can go through and let's first start with 1. We can see this does not share any factors. 2 doesn't share any factors, so it is coprime. 3, however, shares a factor with 15, therefore it is not coprime with 15. 4 does not share any factors, 5 does. 6 shares a factor as well. 7 is coprime with 15, 8 is coprime with 15. 9 shares the factor 3, 10 shares the factor 5, 11 is coprime, 12 shares the factor 3, and 13 and 14 are both coprime. So this now leaves us with the following numbers being coprime with 15. So that is 1, 2, 4, 7, 8, 11, 13, and 14. And we have also listed these down below here. This therefore means that the number of integers up to 15 that are coprime with it is 1, 2, 3, 4, 5, 6, 7, and 8. Keep in mind that doing this is a very long process for large integers, so it becomes very difficult when you're reaching integers such as 143 to list out all the numbers up to it. Therefore, in order to get around this, mathematicians have found a shortcut for counting the coprimes. Euler came up with a mechanism that can easily calculate the count of numbers up to n that are coprime with it. This is called Euler's totient function, wherein phi n is the count. So this symbol here is phi. Note that phi n is also known as the totient of n, and it was proven to be equal to p minus 1 times q minus 1, where p and q are prime numbers and their product is n. Continuing our example that we used in the previous slide, where x equals 15, its prime factors are 3 and 5. So p equals 5, q equals 3. And therefore, if we wanted to find phi x using Euler's totient function, we would say phi x equals 515. We know this equals p minus 1 times q minus 1. So in this example, it's 5 minus 1 times 3 minus 1, which equals 4 times 2, which equals 8. Note that this also correlates to what we found while doing the process manually in the previous slide as well. So now finally, let's go back to our previous illustration that we've been using throughout with these values up here, where p equals 11, q equals 13, and n equals 143. So using these, that means phi n equals phi 143 equals p minus 1 times q minus 1, which are 11 and 13. So this equals 11 minus 1 times 13 minus 1, which equals 10 times 12, which is 120. And so phi n equals 120. This will work for any value n. And again, although we won't be going into the details of why phi n equals p minus 1 times q minus 1, we've linked some websites for this down below in the description as well. So feel free to look up more on this if you're interested. Going on to step 5, we now need to choose a new variable, d, such that d times e mod phi n equals 1. The definition of mod or modulo is the remainder left when the first value, so in this case d times e, has been divided by the second, so phi n. For example, if we were doing 7 mod 2, this would be the remainder left after 7 is divided by 2. 2 times 3 equals 6, 7 minus 6 equals 1, and so 7 divided by 2 would give 3, remainder 1. Therefore 7 mod 2 equals 1. In our example, therefore, we must pick d such that the product of 7 and d produces a number 1 more than a multiple of 120, aka the remainder of 7d when divided by 120 will be 1. There is no simple formula for computing d, so instead you have to iterate through each of the multiples of 120 and see if any of the multiples of 7 are 1 more than these. So first of all, you would check 120 times 1 equals 120. Then you would add 1 to this, so you would do 120 plus 1 equals 121. And then you would check if this resulting value, 121, is a multiple of 7. So in this case, 121 is not divisible by 7, so this would not work. Let's try the next example as well, the next iteration as well. So 120 times 2 equals 240. 240 plus 1 equals 241. And again, 241 is not divisible by 7, and so this wouldn't work either. If we continue to iterate like this, when we reach 120 times 6, we find that adding 1 to this produces a multiple of e, aka 7. So 120 times 6 equals 720. 720 plus 1 equals 721. And 721 divided by e, aka 7, gives 103. And therefore d equals 103. So now we have all of the values we need. We know P equals 11, Q equals 13, N equals 143, phi N equals 120, E equals 7, and D equals 103. So finally, in step 6, we need to arrange these values in order to produce these keys. So the public key will be the pair of E, N. Therefore, in our example, the public key would be 7, 143, this pair. The private key, meanwhile, is the pair D, N, meaning it is 103 and 143 in our case. And thus, we have generated the two keys for encryption. Now you might be wondering how these keys can then be used. In order to send a message using RSA encryption, first the message must be converted into a series of numbers. This is then encrypted with the public key and sent to the receiver. They can then decrypt it with their private key and convert it back into letters. So how do the keys, which seem to just be pairs of numbers, do this? In RSA encryption, the following formula is used with the keys for both encryption and decryption. So in order to encrypt, this formula is used with the public key, and to decrypt, this is used with the private key. Let's say a sender wants to send the simple message H. Following the steps we outlined before, this needs to first be converted into integers. For simplicity's sake, let's say A equals 1, B equals 2, C equals 3, and so on and so forth. So for our message, this gets converted into 8. Next, the public key is used to encrypt. So in order to encrypt our first character, 8, using the public key we created, which is 7143, we need to use this formula. So we need to do our message, which is 8, then the first integer in the key, which in this case is 7, and then do mod the second integer in the key, which is 143. So after doing this, we get the resulting value of 57. And so our plain text would have been H, however, our encoded ciphertext would be 57, and this would get sent over to the receiver in the encrypted form. In order to decrypt after this, so let's just divide these up. This is encryption. And now over on the receiver's side, this is decryption. The receiver would use the exact same formula, just using their private key, which is up here, and that is 103, 143. And they are attempting to decrypt the number 57. So they would use the same model, and they would do 57 to the power of first integer in the key, 103, and then mod 143, so the second integer in the key. Of course, this is a massive calculation. However, if we use a big number calculator, the link to which will also be in the description of our video, we find that the result comes back to 8. And once we convert this back, using the same way we did to convert it into integers, we find 8 converts back to H, aka our original plain text. So in this way, the public key encrypts the message and the private key decrypts it back into the plain text, as we discussed in the theory video. We created a Python program which produces two keys, one public and one private. These can be either random or chosen by the user, and the program is available on GitHub with the link provided in the description. We will be releasing another video in order to talk through the code if you are interested. So with that having been explained, that brings us to the end of the video. Once again, if you have any questions, please feel free to message or comment, and make sure to leave a like and subscribe if you learned something in this video. This topic is quite complex, but once you know the steps, it actually becomes quite easy to understand. Thanks for watching, and see you all in the next video.